Hello everyone, my name is Kirill Danilchenko, and it is my pleasure to present this work covering users by a connected swarm efficiently. This work is my joint paper with Professor Zeev Nutov and my PhD supervisor, Professor Michael Sagan. UAVs, also commonly known as drones, are aircraft piloted by remote control or embedded computer programs without humans on board. Drones have found numerous applications. Wireless communication is essential and has drawn growing attention in recent years. UAV-mounted mobile base station can be used to provide wireless coverage in several scenarios, emergency cases, battlefields, and more. The performance of the UAV-based network depends on the deployment of drones. Generally, the drone deployment problem has been studied so as to find out the optimal three-dimensional position for drones to serve ground users on two-dimensional plane. One of the most crucial strategies on which the researchers focused is on minimizing the number of drones required to provide wireless coverage to all ground users. As a result of that is explicit assumption that the number of drones is at least equal to the number of ground users. In the current work, we consider a more realistic scenario. We focus on the situation where the number of drones is given, and this number is less than the number of ground users. This assumption is reasonable in emergency cases or battlefields where the number of ground users, for example soldier or firefighters, is more than number of drones. Additionally, we assume that ground users have a rank. For example, on the battlefield, it is more critical to provide wireless coverage to the commanding officer than the regular soldier. Due to the fact that the number of drones is significantly less than the number of ground users, we are facing the most crucial question: who should be covered and who should not at any point of time. For a given particular time snapshot, this problem is known to be NP hard. Additionally, we deal with two cases of connectivity between the drones: third party that provides connectivity or drones that provide connectivity among themselves. Now I will present some preliminaries which I will use in this talk. Set, set S of n points distributed in the plane. Each point has a positive weight. Set P of m disks, or squares, of radius r curve. All drones fly at the fixed and the same altitude. All drones have some communication radius r com. Set C contains the center of these disks. So now I will define formally our problems. We start with the covering problems where the connectivity is provided by third party. Static max. Given a set S, place the disk from the set P such that the total weight of points from the set S covered by the disk is maximized, and the dynamic version. Given a set S, maintain the disk from the set P such that the sum of the weights of the points in S covered by this disk from P is maximized under insertions and deletion of points to or from set S. I continue with the current problems where drones provide connectivity between themselves. Connected max, given a set S and the parameter rcom, place the disk from the set P such that the total weight of points from the set S covered by disk is maximized, and the undirected graph imposed on P should be connected. Similarly, the connected dynamic version uh, aims to maintain the disk from P under dynamic updates of set S. Our main goal in this work is to cope with the dynamic problem where the nodes from set S may be inserted or deleted at any time. In this work, we present a first non-trivial algorithm for dynamic version which achieves a quarter approximation solution in log n time. In order to solve Dmax, we use the solution of the static instance of the problem and maintain it under insertion or deletion from set S. Now, I will present some definition which I will use in this talk. We define a grid with a cell size equal R. Cell index, the cell in which point I is located and calculated by following equation. Each non-empty cell in grid will be identified by index. The index pi AB is the result of counterpart function and the cell index is input of this function. In the following algorithm, we present the solution of the static max problem. We divide the area of interest in the grid where each point from the set S falls exactly in one cell. We calculate weight of all non-empty cells and place the drones in the cells having the largest weight. In the following figure, we can see an example when the number of drones is 3. In the left figure, the area of interest divided into the grid, and in the right figure, the drones placed in the most weighted cells, here, here, and here. In the following lemma, I want to present the approximation ratio of our algorithm. Our proposed algorithm achieves a quarter approximation solution in the case of the squares and 1/7 approximate solution in the case of disks. So, I will present the proof of the lemma. We divide the area that contains the set S into grid, which cells size R equals to R curve. The optimal solution overlapping with at most 4m cells in grid. Let's look at the next image. In this image, the grid divides one of the squares from the optimal solution, this one, into 4 rectangles, O1, O2, O3, and O4. That is, each square from optimal solution divided into at most 4 rectangles. Therefore, the number of cells in grid overlapping with the square from optimal solution is 4m. In our algorithm, Hmax, we return the m most weighted cells, then the weight of our solution is at least a quarter of the optimal solution. The case of the disk is similar, but the disk from the optimal solution overlapping with 7 cells in the grid, and the cell size in this case equals square to our curve. A reminder of our main problem under the model of connectivity provided by third party. From time to time, a point is added to set S, deleted from set S, or its weight may be updated. In the dynamic version of the problem, we want to maintain dynamically a set P of disks or squares to maximize the total weight of covered points from set S. The main result in the dynamic version of the problem under connectivity provided by third party is that we can approximately solve dynamic version with a ratio of quarter in the case of squares and a ratio of seventh in the case of disks. Now, I will explain the framework used by us to cope with our problem how to deploy M drones such that the weight of points covered by them is maximal under insertion or deletion of points from set S. Firstly, we place the drones according to the Hmax algorithm. Therefore, in the first step, we solve the static version of the problem. From the previous lemma, we know that the approximation ratio of static solution is a quarter or a seventh in the case of squares or disks respectively. Next, we find among all non-empty cells and not covered by set P, the cells having maximum weight and denote this cell as max C, this one. And among cells covered by P, we find the cells with minimal weight and denote this cell as min C, this one. The main idea of our dynamic solution is after each change in set S, check if max C can replace min C. In order to do that, we must know the weight of these two cells. Note that the min C and max C are two pointers to the grid cells and they may be changed after each update in the set S. In order to maintain dynamically the min C and max C, we propose the data structure. The proposed data structure D is the combination of two data structures. The first data structure keeps the set S and the second data structure contains the set C of square centers and weight of points covered by each square. We denote these data structures by D1 and D2 respectively. The first data structure, D1, is balanced binary search tree built on the x-coordinate of the points in set S. The second data structure, D, is a combination of three balanced binary search tree, T1, T2, and T3. The balanced binary search tree, T1, is a tree where each node corresponds to the weight of cells from grid covered by squares from set P. The balanced binary search tree T2 is a tree where each node corresponds to the weight of non-empty cells in grid, which is not covered by squares from set P. The balanced binary search tree T3, this one, is a tree where each node has a key and value. The key is an index pi AB of non-empty cells in grid, and the value is the center of squares if the cell is covered by square from set P, or none if the cell is not covered by square from set P. Additionally, each node in T3 has a pointer to node in T1 or T2, accordingly if the cell is covered or not. We note that there is no need to store any information for empty cells. The data structure D uses n storage and it can be constructed in n log n time. I will show only one procedure, insertion of a new node in the area of interest. Let Sn be a new point to be added to set S. The insertion of point Sn into D1 takes log n runtime. Next, we calculate cell index of point Sn. We find the cell index AB of point and use it to find the index pi AB. We insert node with key pi AB in T3 or not if pi AB exists and update T1 or T2. There are two options depending on whether exists a node in T3 with the key pi AB. In the first case, a node with key pi AB does not exist. In T3, we will insert a node with key pi AB into T3, and node with key equals to the weight of cells pi AB is inserted into T2. Also, node with key pi AB from T1 has a pointer to the node with key equals to the weight of cells pi AB from 3 T2. The insertion of a new node T1 and T3 takes log n runtime. In the second case, a node with key pi AB exists in T3. Two options are possible. The cell is covered by one of the squares from the set P or not. Therefore, we need to update node with key equals to the weight of cells pi AB in the T1 or T2. The update takes log n runtimes in this case, too. Let P be a square covering min C. We need to check whether or not the location of P should be changed to cover max cell instead of min cell. If the weight of min cell is greater than the max C, we finish. In another case, max C is greater than min C, we have to replace the square P to cover the cell max C. As the result of this, we have to update the data structure D2. The update of D2 includes the value of node V in T1 from min C to max C, and delete from T2 the node associated with the cell max C and inserting a new node associated with the cell min C to T2. The runtime is log n. In this case, the update operation takes log n runtime. Now, I will present our results for the static and dynamic instance of the covering problem when drones provide the connectivity among themselves. We show how to obtain a constant approximate solution to the optimal solution for connected max problem. By increasing the number of drones by factor of square m, we were able to maintain a constant approximation dynamically. In the following theorem, I present the relationship between the general optimal solution and the optimal solution that we are looking for while the drones are constrained to cover the exact cells of grid G. This theorem says that the optimal solution in the grid is at least a sixth of the general optimal solution. Now I will explain the framework used by us to prove this theorem, and after that to cope with our problem how to deploy M drones such that the weight of points covered by them is maximal and the drones are connected. In previous slides, I explained that the optimal solution overlapping with at most 4 M cells in the grid. For ease of explanation, we assume that Rcom equals to R2 equals to Rcov. This requirement can be easily relaxed and does not influence our suggested algorithms. In the next step, I want to present the area divided into grid as a graph. We define the graph representing the grid in the following manner. Two cells are connected in the graph only if they have a common edge in the grid. Now I want to give some example of this representation. On the left side of the image, we can see the area of interest divided into a grid where each point from set S falls exactly in one cell. We assume that two nodes are connected only if they, in the case when the cells with which they are associated have a common border. For example, V1 and V2 have a common border marked by a red line, this one, and represented by node U1 and U2 in the grid graph, and they have a common edge. The node spanning tree of the cells overlapping with optimal solution as T. The number of nodes in T is at most 4m. We decompose the tree T into 6 trees, each of size at most m. So in order to create a tree partition, we will use a well-known partition that can divide the tree into 2 subtrees of size 1 tiered and 2 tiered. We have 4m nodes in our spanning tree. We use recursively decomposition rule above to decompose the tree T into 6 trees, each of size at most m. Thanks for listening. Anybody who is interested may find the entire solution of our paper. Thank you very much.